First of all, Vijay and Xuan Yang Lee. So it's
Thanks.
a real pleasure and honor to give this presentation to this special interest group. So before I start, let me first share my screen and then set my slides okay. So let me maximize full screen mode. So can you see my slide?
Yes.
Okay, thank you. So again, once again, let me thank the organizers of this seminar series. It's a wonderful special interest group, creating a lot of interest in the new topic, which is on OTFS across the globe. And day by day, the number of researchers working on OTFS is increasing. And it's a real pleasure and honor for me to give this talk to this seminar series, and hope to share some of our work that we have recently done on OTFS, in particular transceivers design. So we are moving from some kind of systems related research now, where we are talking about practical transceivers to be implemented for OTFS. So that is when we said that, okay, deep neural networks or deep learning is a new topic. And some of our students have worked on that and contributed to some of the early papers on DNNs for OTFS transmitters and receivers. And I should thank my students, PhD student Bharat, who is a postdoc now, Ashwita, who is my master student, and Sandesh, who is my current PhD student. They all work on combinations of OTFS and DNNs. So special thanks to them. And let me move on to my outline for this today's talk. So Vijay told me that I could take about an hour for talk and maybe followed by some question and answers. So I think this special interest group may have at least some exposure or some research experience or deep research experience in OTFS. So what I'm going to do is briefly introduce OTFS modulation to this group, and maybe briefly introduce deep neural networks to the context that I'm talking about. So neural networks and then deep learning is a very vast subject, but then we will focus on what we are interested in for our purpose, and then introduce the DNNs from that perspective, and then go and show some two examples of use of DNNs for communication receivers, particularly for OTFS transmitters and receivers. One is going to be signal detection. Another is going to be something which is practical, which is IQ imbalance compensation at the transmitter and the receiver, and then conclude with one slide of concluding remarks. Okay, so OTFS modulation is what I'll briefly talk about. So I think this one slide talks about OTFS modulation in a very high level. And first of all, this modulation is something which is suited for doubly selective channel. So when I say doubly selective channel, you talk about frequency selective channel. In addition to frequency selective channel, we are talking about time selective channel, where there is time variations of the channel with, due to Doppler and other reasons. So Ofdm has been popular for channels which are frequency selective, but they've been known to be not so good for time selective channels, where the Dopplers can be very high. Whereas OTFS in a nutshell is good for both frequency selective as well as time selective channels. That is one takeaway. The second thing is the fundamental way the modulation is carried out is altogether different compared to OFDM or any other multi-carrier modulation. So classical modulation schemes, you always deal with signaling in the time and frequency domain. But then in OTFS, we do signaling in the delay-Doppler domain, right? So the basic information symbols are multiplexed in the delay-Doppler grid rather than time frequency grid. So that is point number one. But then time signals are always to be sent over the channel, not any other domain channels. Physical channels are time domain channels. So you have to send the signals in the time domain. So when you say that I'm going to get the information symbol multiplexed in the delay-Doppler domain, I would convert them into time domain and then transmit. We cannot transmit delay-Doppler domain directly into the channel. So you have to convert that into time domain channel. So there are two approaches which are popular, although the second approach is more common in the literature so far. But the first approach is the very standard and very direct approach, where delay-Doppler has a ZAC transform relation to time domain, right? You take a signal in the delay-Doppler domain, to take an inverse ZAC transform, you will directly go to time domain. But if I do the other approach, which is what was introduced in this early paper by Hadani and authors in WCNC in 2017, they took a two-step approach where you do time domain conversion to delay Doppler domain conversion to time domain conversion, and then go to time domain. So first conversion is using inverse symplectic finite Fourier ISFFT. There's a typo here, and followed by Heisenberg transform. So this is what we will be talking about today, because this is what the last 3-4 years research has been focused on. Although new research will be focusing more on this direct approach, which is using inverse Zag transform at the transmitter and Zag transform at the receiver. Okay, so this is point number one. Signaling is done in the delay Doppler domain. Also, the channel is viewed or represented in the delay Doppler domain. So that is point number two, which is different from other modulation schemes where the channel will be often viewed in time frequency domain and so on. And why we are doing OTFS is superior performance compared to OFDM. I think this is something which has kept us going for a long time so far. And I believe this will keep us going for some more time to come, because OFDM is having issues with high mobility scenarios, high Doppler scenarios, and we have to move from 5G, beyond 5G to 6G and beyond. And we are talking about terahertz communications where the carrier frequencies are very high. So even for moderate speeds, we are going to talk about lot of Doppler values, high Doppler values. So OFDM may have to give up, and will OTFS take over? So that may be a question that people will be working on or asking ourselves. But as researchers, we will be continuing to give all the pros and cons of OTFS as a signaling waveform. So this is what I would say, that why OTFS? I just always say that before I say some results, I will say what is the gist of the whole thing. So why OTFS is important is OTFS performs better than OFDM. And this is a figure which shows, without giving details, if I have a system where there is a carrier frequency of 4 gigahertz, and I have a subcarrier spacing of 15 kilohertz, and I have a frame size where, when I say frame size, it is in the delay axis and Doppler axis, bins in them, M bins in the delay axis, N bins in the Doppler axis, to be 12 and 7. And if I say in the delay Doppler domain, I have 5 different paths represented in the delay Doppler domain, and you have the maximum speed of the user is 500 kilometers per hour. For this carrier frequency, it is going to be 1.875 kilometer at the hertz of Doppler, and the modulation is BPSK. Under this setting, if I do a MMSC detection at the receiver, this performance comes up. This blue curve is the OTFS performance. And for the same system or a similar system, you do OFDM and then plot the OFDM performance with the MMSC detection, you have substantially poor performance. And that is because the intercarrier interference is going to be caused because of this 1.85 or 1.875 kilohertz Doppler. So this is one motivating figure. Okay, so this is a CISO OTFS system. And next is MIMO OTFS versus MIMO OFDM, because MIMO is part and parcel of any standard these days beyond 4G onwards. So if I look at a 2x2 MIMO system and then look at a high mobility scenario where the maximum user speed is about 500 kilometers per hour and 1.8 kilohertz is the maximum Doppler, and the frame sizes I consider here are much more than 12 and 7, which is 32 delay bins and 32 Doppler bins, and you have message passing detection, which is a low complexity detection for getting the detected bits out. So you have OFDM performance to be this blue, OFDM performance to be this. So in MIMO OFDM MIMO setting, MIMO OTFS is better significantly compared to MIMO OFDM. And then not only in terms of bit error performance under ideal conditions, let's talk about some aspects of non-idealities in the transceiver, because that is one of the focus that we want to focus on this lecture. Suppose if I have a transmitter which is going to show I and Q arms, and this is an ideal transmitter. The gain on I channel and the Q channel, they are same, unity in both the arms. And the phases on the I arm and the Q arm, they are perfect, meaning cosine and sine, they are 90 degrees apart, and there is no phase imbalance between I and Q. Under these circumstances, if I send a constellation at the input, which is I show here as four blue dots, they will come in the same locations at the output as red dots, and they are not altered. But suppose if I say that there is a imbalance between the I arm and the Q arm, and there are two types of imbalance that you can talk about. One is the gain imbalance, another one is the phase imbalance. So I characterize that using delta G at the transmitter T and delta phi, that is phase imbalance at transmitter. So because of this delta G and delta phi, what essentially will happen in a practical transmitter is this 4-QAM modulation alphabet at the output of this, because of this delta G and delta phi, will be skewed depending upon the amount of delta G and delta Q as these 4 red points. So even before you enter the channel, you are getting distorted and you are, degraded, in terms of the transmission. So this is a practical issue. And suppose if I ask this question, if this is a practical issue, how OFDM does and how OTFS does? And this is the result, right? If I compare based on our work, which is reported recently in PAMRC, so we show a comparison of two systems. One is OTFS, another one is OFDM. All other system parameters being the same. This figure shows my gain imbalance is 0. That means no gain imbalance, but I have phase imbalance on the x-axis, and I plot the BER. So you can see that OTFS is one order clearly better, particularly for phase imbalances of 40 degrees and below compared to OFDM. And the other way, I keep the phase imbalance to be 0. That means there is no phase imbalance, but then I have gain imbalance, and that I vary from 0 to 1. So here again, you can see that OFDM is far inferior compared to OTFS. So which is to say OTFS is more robust to transmit IQI than OFDM. I'm not doing any compensation for IQI. You may ask, you can do IQI compensation. So that is a different question. But even without a compensation, what this result shows is OTFS is more resilient or robust to IQI. And this is a similar figure for receiver IQI. Just like you have the transmit chain, you have the receive chain. In the receive chain between I and Q, you have the delta GR and delta phi R to be the imbalance parameters. And if I vary the phase imbalance, keeping the delta G 0 and gain imbalance, keeping delta phi R to be 0, you can see again, OTFS is significantly better. So this is one of the reasons why OTFS keeps coming again and again in the public domain, more and more as days pass by. Not only that, one more practical issue that we will be talking about as we move from 5G to even 6G is move from sub-6 gigahertz carrier frequency to millimetric wave carrier frequencies like 28 gigahertz and 60 gigahertz or even terahertz. Okay, so one of the practical issues, if you talk to RF engineers, they will say that at RF frequencies like millimetric wave, phase noise is going to be a key issue in the oscillators, for the local oscillators, for the transmitter and the receiver. So what I have shown here is the phase noise characteristics of oscillators for different carrier frequencies, 4 gigahertz, 28 gigahertz, and 60 gigahertz. And this is the frequency offset with respect, this could be the center frequency. And moving away from the center frequency, what is the phase noise power spectral density in units of dBc per hertz? So it goes like this for 4 gigahertz. But as 28 gigahertz carrier frequency, if you use, it is going to be even more. 60 is going to be even more. So in other words, there is a problem of phase noise. And the phase noise is going to cause, again, degradation in the signal at the receiver, even at the transmitter. So then we ask the question, how phase noise affects OTFS in comparison with OFDM? So this is again a result that we have published recently or a couple of years back, where we said we take 28 gigahertz carrier frequency and bandwidth being 10 megahertz, subcarrier spacing being 78 kilohertz, and frame size being more practical, 128/64, BPSK modulation. And there are some phase lock loop bandwidth and other things that we have been taking into account. And a rise factor of 13 dB is considered because in millimetric wave, we may have a line of sight component in addition to diffused components. So it could be a rise distribution of fading. So we considered some rise factor. And you can see that the BER that we end up seeing is OTFS is blue and this is red, Ofdm. So again, from in the presence of phase noise, which is more critical as we go along very higher and higher carrier frequencies, the waveform should be inherently robust. So inherent robustness is there in OTFS compared to Ofdm. Now there may be a question, these imperfections and these practical issues, can it be addressed by implementing some counter measures to offset the effect of phase noise, offset the effect of IQI? Yes, you can do. You can do for both OTFS as well as Ofdm or any other waveform in general. But the newer emerging trend is whatever you have done in the classical or conventional way of doing things, IQI imbalance compensation has been there, phase noise compensation has been there, but the new approach is to use deep learning or deep neural networks. So that we will come to the last 1/3 of the talk. So this gives me an answer why OTFS is important, right? I ask myself why OTFS should be important. I feel on any performance measure or any scenario under which you test competing waveforms with OTFS, OTFS comes always ahead. So that has been our experience, and that has been confirmed by many people around the world in research. Okay, so this slide shows moving forward two ways of implementing. This first one is the direct approach, as I told in the first slide. This XKL is essentially the information symbols, okay? And K is the delay index, Doppler index, and L is the delay index, okay? So in other words, this is a two-dimensional grid having K as the Doppler index and L is the delay index, and you mount information symbols on each of those grid points. And take inverse Zach transform, you directly get X of t, which is a time domain signal, continuous. You can transmit through the channel, which we say that it could be doubly selective. And I may want to represent that in the delay-Doppler domain, that we will come later. See the time domain signal Y of t, and then do the Zach transform, you will get YK of L, which is the delay-Doppler. So this, we believe, could be one focus area of future work, because we have focused too much in the initial days of OTFS research in this two-step approach. Because Adani and others, when they wrote the paper in 2017, they did delay-Doppler to time transformation through time frequency in between, because this time frequency to time frequency is a legacy system, which is Ofdm or any multi-carrier system. And on top of that, you can do this ISFFT and SFFT. So in other words, it is an overlay on the existing multi-carrier waveform, which is 2D time frequency modulation. So, but it is much more simple to use this direct approach. So we may be focusing more of our research in future on this type of modulation directly using inverse Zach and Zach rather than this. But for today's talk, many of the papers are based on this two-step approach. I will continue with the two-step approach, where you start with the delay Doppler, that is small xkl, and convert that into capital X, which is the symbols in the time frequency domain, where n is the time axis, m is the frequency axis indices, and x of t is time, y of t is time, and nm again time and frequency indices of the received symbols, and small k and l delay Doppler and delay indices on the delay Doppler domain. Okay, so another carrier wave, which I think many of you will be familiar, is what is good thing about this OTFS is it looks the channel in the frequency in the delay Doppler domain rather than time frequency domain. So three things are very unique if you look at the channel, which is time varying, that too rapidly time varying, but observe that in the delay Doppler domain. Three things are very unique. One is the channel becomes compact. When I say compact, the representation of these two diagrams is illustrative of what do I mean by compact. This plot, which I call this as H of TF, is the channel response, which is in the time frequency domain. It's channel impulse response as represented in the time frequency domain. As you can see, it is all over the place in the time frequency plane. The variations are all over the place. It varies in the time axis, it varies in the frequency axis. If you have to characterize and then estimate this channel, you have to estimate a lot of parameters, and we have to continuously track that, which is a very difficult task. Whereas if I see the same channel in the delay Doppler domain, as I show it here, Doppler domain here and delay Doppler domain, you have only few peaks. That is what we mean by compact. Instead of having, components all over the grid. In the delay Doppler grid here, you have very few dominant peaks. Sparse. Again, much of the grid points are having very low response values or zero values, so it is sparse. And stable, because these coefficients which you will see, the delay Doppler and the coefficients, they will change very slowly with respect to time. Although in real physical situations, they will be varying very rapidly in time, but view that in delay Doppler, it is very slow. So 3 parameters of a channel are important. You have the tau I, which is the delay of the ith path, Doppler of the ith path, and the fade coefficient of the ith path, and there are capital P of such paths. And this number of paths are due to various reflectors around the transmitter and receiver. Okay, this is to show the grid which we are interested in. So we are talking about time frequency modulation, which is the time frequency grid. So when I want to transmit a time frequency signal, I have to use certain amount of time and certain amount of frequency to send one frame of time frequency grid. So here I have n time slots, each having t seconds. So the time axis is nt seconds, and one slot is t seconds. And likewise, I have delta f to be in my subcarrier spacing or frequency bin width in the frequency axis, and I have m of them, capital M into delta f being the bandwidth of operation. So you have nt seconds and you have m delta f as the bandwidth for signaling. So a classical OFDM or multi-carrier signal will mount symbols on this grid and then transmit it in nt seconds. But in OTFS, what you do is mount it on the reciprocal grid, which is the delay Doppler grid, where I have the Doppler here and delay here. So there are again n grid points here, but the resolution of the delay, the Doppler is 1 by nt. Likewise, there are m delay bins, but the delay resolution is 1 by delta m. And the relation from here to here is essentially 2D SFFT. If I go from time frequency to delay Doppler, the relation is two-dimensional symplectic finite Fourier transform. On the other hand, if I mount the symbols on this red grid, all I have to do is just go to the time frequency grid using this 2D inverse SFFT. That is what this figure was all about. That was what this figure is all about. Mount it in the red grid, do ISFFT, go to the blue grid, and then convert that into time, which is Heisenberg transform, which is a 2D generalization of the Fourier transform, and do the reverse on the receiver. Okay, so this is about the grid. And essentially, you even in delay Doppler, to send one OTFS grid worth of symbols, which is mn symbols, you need nt seconds and m delta f bandwidth. Okay, so I will come to the input-output signal. I will not go through the math that is there in the literature quite a bit. And I will simply say, what is YKL, which is the output of my receiver in the delay Doppler domain. So that is going to be related to my XKL, which is my transmitted symbols in the delay Doppler domain. And HI prime, I have this HI e to the j 2 pi nu I tau I. And this is the input-output relation, this V being the noise. Okay, this derivation has been done in paper by Ravi Teja and Viterbo quite some time back, and it is widely used by many researchers now. That is what I'm showing as the input-output relation in the delay Doppler domain that you are interested in. Pictorially, what this equation shows is given by this diagram. So you have this X, which is the QAM symbols or PSK symbols mounted on the delay Doppler grid, and the channel which is represented in the delay Doppler grid, which is going to be sparse and compact and slow, right? And you do the 2D circular convolution of these two as per this equation, you will get the output YKL, right? So this YKL as a function of this H and the X can be written in a compact form. I would refer you to go through the paper by Ravi Teja, Fan and Viterbo to get this form, Y equal to HX plus V. So essentially X is the vector of all Mn symbols, H is an equivalent channel matrix, and Y is the observation vector, and V is the noise. So I assume that this is the starting point for us to do the signal processing from now on, right? I will assume that people have already used it, or if they want to use it, there are reference papers, and quite a few papers have followed that. And the interesting thing is this H matrix, which is the equivalent H matrix, has a certain structure, which is to say that H is a block circulant matrix with circulant blocks, each row having only P non-zero elements. So that means the H matrix is going to be a sparse matrix. So this has been exploited by researchers, including us, to devise very low complexity transceivers, particularly MMS receivers. Okay. So now with this, I have spent a little bit more time than I wanted about the importance of OTFS, where it scores over OFDM, and what is the difference between the one-step approach and the two-step approach, and where we should go from now on beyond two-step approach to one-step approach, and then the system model that I'm interested in. So keep the system model for a while. Now let me quickly go through where DNNs come in processing this y equal to hx plus n. So a general slide of interest is deep learning is very important. Everybody knows. We don't have to talk big about it because everybody is aware that deep learning, machine learning, artificial intelligence are big. So we will assume that. But our interest is our communication system engineers or communications theory people. We want to see what DNNs or deep learning or machine learning can do for us. So early work in this area has been, given in the references that I have put in this slide. And basically 2 points I would like to tell my students and my collaborators, or even I would like to see in that context. So what does deep learning do for our communication transmitter and receiver? So a first approach is to say that I will change a conventional implementation of a transmitter functional block using DNN. For example, I can change my channel encoding block using a DNN implemented channel encoder. I can design codes using channel DNNs. Or at the receiver, I can do signal detection block to be done using a DNN. Or channel estimation, I can use DNNs. Or at the transmitter, I can use DNN-based precoder. So I can take one block out, put a DNN which is suitable there, and then see whether there is any good things that can happen. That is one approach. Another approach is autoencoder approach, where you see the end-to-end system as a whole, which can be designed by neural networks altogether rather than having individual blocks to be implemented by DNNs. So that is an end-to-end communication systems approach without traditional communication blocks. Both have been addressed and both have been shown to be promising. Both have been shown to be promising. And a general set of things that are important for us right now, what we have in our research group, which is communication research group, we have GPUs in our labs. Maybe 4 years back, 5 years back, it was only higher end, PCs. But then these days now we have GPUs, and that is to say that hardware has evolved more and more to shorten the training times. All the learning techniques, we have a training component and a testing component. And then what we are interested in is really testing, which is what is our communication operation in real time. That is our testing phase. But for that, you have to train, and train in a lot of other applications can be offline, and it may not be time critical, right? But for us, we have to make sure that whatever we train, it should be finally be useful in a real-time testing phase when communication goes on in real time. So the interesting aspect here is the training takes time. I think many reviews, when you submit a paper based on learning to communications theory and journals or even conferences, this training is going to be a killer, right? So many a times it is true. But the point is, once you train, you freeze the coefficients or weights, then I think it can be stable for long time, right? And because of that, it is still possible for us to use DNN approach in communications as well. And training data, where will we get the training data? Images, social media data, a lot of other applications, they have a lot of experimental data for training. But benefit for communication engineers is we can generate synthetic data using our models, channel models, fading models. We can generate synthetic models, and there is no limit. We can simply generate as many training samples as you want. And last point is, whenever there is an assumed model for our communication system or a channel or something, right? That model, if it is not good, the resulting performance is going to suffer, because we will assume a certain model and devise an optimum solution for that from a theory point of view. But then go to the practice, that model is not going to be true. Then the optimum deceiver that you decide or optimum code that you decide need not be performing in an optimal way, because in practice that, there is deviation from the standard model. So in other words, you have to make sure that the models are good. If the models are not good, because they are deviations, there are imperfections in practice, deep learning can be very good, because deep learning has been shown to be very robust to such deviations from the standard models and imperfections. I will show some examples as we go along. So one slide or two slide activity about what we are going to show later as signal detection using DNNs. So this is the basic neuron, which is a component of a network. So neuron input side, you have n inputs and one bias factor, and weights with which these input come in, and then do a weighted sum and call that as a z, and do an activation function, which is a nonlinear function on z, and call that as y hat. Okay, so this is the basic neuron, and what I have here is inputs and an output, and in between you have a weighted sum, and that weights are not known, and essentially I have to train and get the weights for these neurons, and not only one neuron, multiple neurons, as we will see in the next slide. Okay, so this nonlinear activation function is crucial, because by doing this neuron, you are essentially trying to mimic the real world, which is not necessarily linear in most of the times. So this is the basic component which is trying to mimic the so-called practical complex world. Okay, so now not only one neuron, you have a collection of neurons. So what is the objective of a neural network is the following. I have a input side to a system. I have an output side to a system. And I want to model how this system is going to do. Given the input, it is going to give a certain output. So this inside, whatever you see here is collection of neurons and interconnecting connection between those neurons, which is the network. Okay, as you can see here, there is an input layer having multiple neurons, output layer, certain number of output neurons, and in between what we call there is hidden layers, and hidden layers also have multiple neurons. And in one network, we have a structure which is called fully connected network, where every neuron is connected to every other previous stage neuron. So this is an architecture of a fully connected neuron, which is also called a network, which is called deep neural network, when you have more than 2 or 3 layers. So now the problem that we want to solve is find out these weights on these edges. Whatever we call in a single neuron as this weights, we will have a network, and you have a collection of weights to be optimized. And to do that, we will do in 2 directions. First, you do a forward pass from the input layer to the output layer, and that is following this operation, right? You give input, do this computation of z, and then take the activation function and then get the output. So that is the forward pass, that is finding y hat from u. After coming here, you want to go back. This is assuming in the forward path, assuming a certain weights, you will go to in the forward direction. And in the backward direction, for a given y hat that you got, compared to a ground truth, you want to minimize the output y hat with respect to y, and then go back and optimize and get this updated weights. And once you get the updated weights, again go in the forward direction using the forward weights, and you get the y hat. And again, find the difference between y hat and the ground truth y, minimize that by doing the optimization in the backward direction. So this is the standard practice, okay? And to do the optimization on the backward propagation, you have to use a function which is a typical function of interest, and this is loss function. Typically mean square error or binary cross entropy or loss functions. So that is the idea. So in communications, this network that we are going to decide for signal detection or channel estimation or IQA imbalance or whatever we want to design, you have to design the input layer, number of neurons in the input layer, what you are going to feed as input to the input layer, that you should know. And at the output, you should know what are the things that you are going to get at the output and what are the output variables of interest. And you have to say how many hidden layers you're going to give, and how many nodes in each hidden layer is going to be given, and the activation functions in each of these. So your definition of a neural network for your purpose is you have to define the input layer and the number of nodes there, and the inputs, output layer and the number of nodes there, and the variables and the number of hidden layers and the corresponding weight activation functions and so on. So there are, other than this fully connected DNN, which I talked about, convolutional neural network, recurrent neural network, which are different and they will be useful for different purposes. But I think within this talk, I will restrict myself to fully connected DNN, which I described in the previous 2 slides. And again, there are different platforms which you can use for doing this DNN implementations using TensorFlow and widely used framework. PyTorch, again, Facebook, it's a competitor to TensorFlow. And Keras, I think it is again a Python-based thing, which is on top of TensorFlow. So I think it's getting richer and richer, both in the hardware as well as in the software framework. So now let me give 2 examples of this use of this DNN in OTFS. Okay, so I gave y equal to hx plus v, and let's start with that. The detection problem is given y and h, I should get an estimate of x, where x is the symbols and y equal to hx plus v is in the delay-Doppler domain. So in some sense, we are talking about a DNN to do delay-Doppler signal processing to get the symbols in X. Okay, I'll talk about 2 detection approaches. One, which is an approach which I call this as full DNN approach. What I'm going to say is I will define the input layer to be the y vector, because that is the observation vector for me. So I will feed the y vector to the input of the neural network. So this y vector is going to have mn complex values, because the y vector is of size m into n, corresponding to mn symbols that you transmitted at the x vector. Now, I will take that as into a real model, and then real and imaginary I will cascade, and then I'll say 2 into mn neurons at the input. So that I have defined. And the output, what I in one approach do is I will do one output neuron for one possible OTFS signal vector. X is an OTFS signal vector, and there are multiple vectors which are possible. For each of the possible vector, I will give one output neuron. So in other words, size, if A is the alphabet, A power mn is the signal set, and size of that signal set is the number of neurons I'm going to give at the output layer. So it is going to be exponentially growing in mn, but nonetheless, it is going to be a starting point. And it is going to give high complexity, but it is going to be a one large DNN, okay? 2 mn input neurons with y as the excitation, and output is going to be one neuron corresponding to one OTFS signal vector. Okay, so this is one approach. Another approach is going to be, I do not want to see this entire OTFS signal vector, but I will see one symbol in a X vector and give one small DNN for that. Okay, use multiple small DNNs, but one small DNN for each of the coordinate in X vector. So the advantage is you will have only mn DNNs, but the output layer corresponding to each DNN could be the size of the alphabet, which could be small, right? There it was exponentially growing, but it is now here very simple, okay? So the complexity is reduced. So I have defined 2 approaches, one at the OTFS signal vector level, another one is at the OTFS QAM symbol level. So one is very complex, another one is less complex. Let's see how it is going to look like. So this is the diagram that I want to show as the full DNN approach. So you have y1r to ymn I. So the real mn of them, imaginary mn of them, these are the input nodes. And these are the output nodes, which one blue node for each of the OTFS signal vector. Number of hidden layers that I will define as we go along. But what I will use here as activation function is going to give me a probability value for each of the OTFS signal vector, adding up to 1. So that probability which is having the highest, that OTFS signal vector which is having the highest probability, I will choose that, and that I will get back that as the h hat, x hat. So that is the idea. So now how you define insight as we go along, we will see in terms of numerical numbers. But this architecture needs learning large number of parameters. When I say learning large number of parameters, it is going to be the number of weights that we are talking about. Number of weights that we are talking about, that is going to grow in exponential terms. Okay, so this is the other architecture which I talked about. This suppose if I say that input side is the same, number of neurons at the input side is the same, but this is a DNN by itself. And this is corresponding to x1 hat. That is the first symbol in the X vector. And there is one DNN to estimate a QAM symbol. Here I have, for all QAM symbols, there is one large DNN. Okay. Whereas here I'm slicing the problem at the symbol level and I put a small DNN for one symbol. Symbol 2, another DNN, and so on. The output for each of these small DNNs is going to be size of A. A is the alphabet, size of A is the number of output neurons, and that their probabilities will add up to 1 as softmax outputs. Choose that symbol node whose probability value is maximum, take it out, and then declare that as the detected symbol. So this is advantageous in terms of fewer number of parameters to train. So now let's see how we are going to decide the various hidden layers and the number of neurons. See this, I have a standard IID Gaussian noise model. V is Gaussian, and 4 gigahertz of carrier frequency, delta F, which is the subcarrier spacing, 2 delay bins and 2 Doppler bins, and 2 delay-Doppler paths and BPSK modulation. This is a setting I have. And I will take one instance of a relay feeding channel to make my DNN to work and then make some insights. Okay. And in the full DNN, this is the structure. This is the architecture. I have the input layer, I have the output layer, and in between I have I have only one hidden layer. I have only one hidden layer. So you can see here, number of hidden layers is 1 in symbol DNN as well as in full DNN. So the ReLU is the activation function in the input layer, and ReLU is the activation function all but the last layer, and last layer has softmax as the output layer. So in other words, this is the architecture. And for symbol DNN also, there is only one hidden layer with 4 nodes, and ReLU and softmax as the activation functions. And all other things like Adam is an optimizer, which is used in the backward propagation to do the optimization done. And the loss function that we use for minimization is the binary cross entropy. And we train the network. When I say train, you realize multiple instances of Y for multiple realization of the X, H, and N, and then feed these multiple realizations of Y and X into the network and train all the weights in all the layers. And you train the network at a given SNR of 10 dB. And then we see that it works for a range of SNRs of interest. Although we train it at a certain dB of SNR, it works over a larger range of SNRs of interest. So use certain number of training examples and so on. So this is what we do, right? This is the symbol DNN. As you can see here, this is input-wise, they are the same. Output-wise, you have 2 power mn, which is 16, whereas here it is only 2 because it is BPSK. And as I can show you here, all the 3 detectors that I show, one is the maximum likelihood classical, and the other one is symbol DNN, another one is full DNN. All are roughly getting the same performance because they are all equally good, right? DNNs has the potential to reach the maximum likelihood performance, which is the classical best, okay, under IID Gaussian. But see here the complexity, maximum likelihood is complexity-wise 1088, whereas symbol DNN is just 300 here, full DNN is 564. So the beauty is that you can go close to ML detector, but with lesser complexity. And compared to full DNN, this symbol DNN, which is going to take advantage of the less number of training parameters, the complexity is less. Okay, so where does this take us? Is it one more approach? There are several detectors which will give you near optimal performance. Is DNN one more, or it is something more, right? So the idea is it is something more is what we would like to believe. And that is to say, when I showed this plot here, this is assuming the noise is IID Gaussian, okay? But in practice, there are reasons for us to have deviations from this IID Gaussian model for noise, okay? Under such circumstances, we have seen that the DNNs are going to do better than the optimum. Okay, so this is what I would say. I will consider two cases where non-Gaussian noise I will subject these three detectors, and correlated noise I will subject. Okay, so first we will say non-Gaussian noise. See, this plot is T distribution noise as well as Gaussian noise. The PDFs look very similar, but they are different. And the T distribution has a parameter phi, nu, and depending upon that parameter, it will be going close to Gaussian or deviating from the Gaussian. Suppose if I assume the noise to be not Gaussian, but T distribution with a certain parameter, we would like to ask what happens. And this is what happens, right? When I have this ML detection, this is the performance. This is the performance in the IID Gaussian case. But the moment T distributed noise comes in and use the same ML detection rule, which is the Euclidean distance based measure for scalars and vector norm minimization for the vector single set case, the degradation happens because this is optimum only when the noise is Gaussian. If it is not Gaussian, then you're going to lose performance. But instead, if I use learning, and that is symbol DNN, you can have significantly better performance. So this, I think, is one major carry away. Rather than simply applying a DNN technique and then say this is yet another technique, I think the judicious thing to do is it really going to be beneficial in addition to your standard set of things that you will get as a deep learning thing? Will you get anything substantially different? This is one instance where the distribution of the noise, if it is not what you assumed, then learning is useful because it learns the channel quite well or the underlying model very well rather than the assumed model. So this is one advantage. Another advantage I can say that this is again for a different set of detectors for larger M and N values using MMSE detection. Same. The next is correlated noise. See, correlated noise is something which we often come across. Suppose if I have MIMO systems and if I have spatial correlation, then we have seen that the noise is not IID Gaussian, and this noise vector, which is at the receiver, is not going to be an IID N, but it is going to be a correlated NC. And this N, capital NC, is going to be the correlation matrix. And this is a model of a correlation matrix where this rho is a correlation coefficient and it is not identity matrix. If this were to be an identity matrix, it is IID. But this is correlated, this correlation model as an example we take. And if you use the ML detection without using the whatever the covariance matrix of the noise vector in the ML rule, you will degrade significantly poor, but DNN will do well. So this is the diagram that shows that. So basically ML detection, IID Gaussian is this blue one, and then it gets degraded. So let me put it this way. This is, okay, so rho equal to 0.4. When rho equal to 0.4 and ML detection, which is 0.4, which is this square, okay? Rho equal to 0, this is 1 performance, which gets degraded when correlation is there, but DNN is going to do quite well. So this is another point. Okay, sorry. So this is another reason for us to believe that this can be doing, DNN can do quite well. Okay, so last one which I want to highlight and give some insight into this DNN approach to IQI is the transceivers, transmitter and receiver. Okay, so as I said, this transmit IQ model is something which we are worried about, and there are standard techniques available. And in OTFS, we also saw that it is more robust compared to Ofdm. But I want to compensate this, right? There is an effect of delta G and delta T at the transmitter, which is skewing our constellation even before we are transmitting it. So what we are transmitting, what we are supposed to transmit is a X vector, right, with symbols from this alphabet. But what we may end up doing is this red one on the air, which is what I call this as XIQ, which is the distorted alphabet or the transmit vector, which is going to be the combination of X and its image, which is X conjugate. So you create this image because of this delta G and delta T. So there's going to be a coefficient, which is alpha T and beta T, which are complex numbers, which are functions of this delta G and delta phi as given here. So this alpha T is a complex number depending upon this phase and gain imbalance. Beta T is like that. And we have this X conjugate to be created by the imbalance. So what you are essentially transmitting is XIQ, and what you are observing is Y equal to HIQ, XIQ V. So this is a issue. And this causes degradation, and we call this as interference suppressant ratio between this beta T magnitude square divided by alpha T magnitude square. But the message is that it is going to hurt our performance. Now, something similar happens at the receiver. You have received alphabet, and if it is passed through a received chain, and that is also going to get distorted. That's also going to get distorted. And here there is delta GR and delta phi R. Okay. And instead of observing Y, I'm going to observe YIQ. Okay. And this alpha R and beta R are functions of this relative phase and gain imbalance at the receiver chain. So if you have an ideal transmitter and even non-ideal receiver, you will have a problem. If you have ideal receiver and non-ideal transmitter, you will have a problem. In practice, both will be not ideal. So that is the problem that we want to solve using DNNs. Okay. So this is one DNN. If I can describe, it'll be a good point where I can just spend the last 1 or 5 minutes. Okay. So this is the DNN which we have devised to do the IQI compensation at the transmitter. Okay. So let me tell you what it is. This blue box is the hardware. Okay. Your transmitter, OTFS transmit chain. Okay. And if I pass this A alphabet, right, through this chain, it is going to be distorted. This A is the blue constellation in the diagram. This AIQ is the red constellation in the diagram. So I know this. Based on what my hardware is, I know this A to AIQ. This is the distorted constellation. So A is the alphabet, AIQ is the transmit IQ impaired alphabet. Okay, so that I can get. Okay, now my idea is I do not want to transmit. This is the transmit chain. This is the actual transmitter. This is the learning part. This is the transmitting part. Okay, now X is belonging to A is what you would want to transmit, but this transmit chain is imperfect. So what you may want to do is pre-compensate by using a alphabet which is a different alphabet, and that when it goes through this chain is going to give me transmit alphabet which is close to A. Okay, so I'm not going to send A directly to this box, but I do a mapping from A to A compensation constellation. That constellation is going to be different from A, but when A compensation compensated constellation goes through the channel, it will be rotated back to ATX, and ATX, which is the transmit constellation, will be close to A. So that is the idea. Now, the problem for the DNN is to find out what is the compensating constellation. For a given constellation A, what is the compensating constellation, which you can learn using a DNN. And for that, it is very easy. So you have AIQ, which is going to be the impaired constellation. And this you can configure using input layers and output layers. But the training you can do by creating random values of this delta GT and delta phi T and create this output, this XIQ, because for a given delta G, delta phi, create this alpha and beta, and then generate this XIQ. So that is for synthetic, for synthetic generation of data. So you generate this, and this compensation constellation is going to be given by this. So this is an expression that you have to derive, where if I have A is the ideal one, but it is distorted by this alpha T and beta T due to IQI imbalance, where delta G and delta phi are inside, what is the solution to bring back to A, right? And that is a compensating vector or alphabet. So this relation also you use and generate the corresponding compensating constellation. So in other words, for a given delta G, delta T, create the compensating constellation by synthetic means, train this network so that the input is AIQ, A comp pairs. My ground truth is what is this A comp prime, and then try to minimize the difference between the true AI comp and the actual output of the DNN, and then get all the weights frozen. So once it is trained, I will get a compensating DNN. So this is offline. So once it is trained and you get a compensating alphabet, you pass this X belonging to A through this mapping, and that map will give compensating symbol output, and that you pass it through, that will be rotated back, and then you will get this. So that is the idea. And this we have done for BPSK 4-QAM and 16-QAM. As you can see here, we have defined the number of input neurons, output neurons, number of hidden layers, and activation function in the hidden layer, activation function in the output layer, the optimization that is to be used. And this is again a regression problem. So use mean square error as the last function and do all these things and see this performance. So this, I think, picture is illustrative. So look at this. Whatever I described in words, it is in picture. It is easy to see. It is a 4-QAM constellation. A is red circles, 1, 2, 3, 4. It's a standard ±1 ±j, 4-QAM. And I say that with delta G equal to 0.4 and delta phi equal to 40 degrees. So that is fairly large imperfection. And this pink stars happen because they are the skewed ones. Even before you are going to go out, this is going to be skewed like this. But now your DNN has given you a compensated alphabet, which is this blue. This is the DNN output. Okay, this is the DNN output. Now, what you end up transmitting is not A. So you do A to A compensating map, and then transmit this blue. But when blue goes through the actual transmitter, what will come out is this ATX, which is X, small x. That is what is here. So it is rotated back. So in terms of performance, what you can see here is when you say there is no ideal case, no imperfection, this is the performance. But imperfection without compensation, it goes up. But with this DNN-based compensation, it comes back again to original, very close to that. So that is the idea. So you can do offline training and then freeze the coefficients of the DNN. And once that is, this IQ imbalance parameters are not going to change very often. So it can go and then do that mapping and do the compensation, and you are going to get back the performance. And this is the structure of the alphabet network. Okay, so I would say that a similar thing can be done for receiver IQ imbalance. I will just let you go through the paper if you are interested. We have done in 2 stages: estimate the parameters, which are the imbalance parameters, and then correct it. Okay. The last one is again good performance after compensation. And the last one is channel estimation. I think this is very important because delay-Doppler channel estimation is important. And what we have done in this work is very interesting. What we say is you have no explicit channel estimation, okay? But we say that channel training, okay? So any transmission, when you do that data transmission, prior to that, there will be a pilot transmission during which you estimate the channel. So what now we say here in this architecture is you train a DNN, right, with both pilot as well as data together. My Y as the input to the network is both pilot and data together, and solve for X, which is the solution that we want to do. So it is channel training and detection together. So it's a single problem by a same DNN. Normally we will do channel estimation separate and detection separate. But this DNN, what we are now proposing and seeing good performance is train the network for doing channel training as well as detection together. Your objective is to get a good estimate of the data, which is detection problem. But in the training itself, you embed the pilot inside that, and that knowledge goes inside the DNN filter, and that comes out as detected output. So this is an interesting approach, and we see that this channel estimation based on this DNN, the performance is very good, particularly in the low pilot SNR domain, right? At high SNRs, you don't have much issues, but this learning-based or training-based approaches are doing quite good in the low SNR domain. For details, I will let you to go through the papers. Maybe at this point, I will say that it is a very promising area. Channel estimation, particularly for low pilot SNR regime, this deep neural networks or deep learning ideas can be quite useful for OTFS. So that is captured in this work. And this is the overall transceiver. If you can see that, this is what we did. This is the transmit side, one neural network you can do for doing the compensation at the receiver after the channel. This is the channel. After the channel, you do the receiver IQA compensation. After you do the receiver IQA compensation, you do the channel training and detection. So put together, you have integrated DNN-based transceiver, which each of these modules, are devised in a way to meet our requirement of compensation as well as detection and training requirements. So they seem to work quite well, and it's quite promising for future work in this area. So this is another set of plots which convey the same thing as what I've shown. Particularly, this is a 10 dB SNR for pilot, and this is DNN. This is ideal. These are other techniques. Other techniques, when they do not so good, but DNN-based things do quite well. And that is a promise that we hope that will, make us search a little more in the deep learning literature for communication receiver design. So that's all I have to say, except that now I will make some final concluding remarks. OTFS is a promising new modulation in waveform, and it has been getting good attention. And DNN is what I think is a good companion tool for OTFS, because for practice, where conventional approaches are not adequate, where there are model mismatches, DNNs can be very useful. And they are good for dynamic environments. Design and optimization can be done very effectively in dynamic environments using these tools. And some of the important things that you have to keep it in mind is we need to pay closer attention to training requirements, how to define the networks, how to optimize them, and how to get them in good complexity terms, as well as in real time as offline. All those things are open for research. And we have overall, with a combination of OTFS and this deep learning, we have a very good combination for setting problems for future research and investigations. I think with that, I will stop and thank you all for listening. And it's about just one hour plus a little bit. So thank you for your attention, and I can take questions if there are any questions.
Yeah, thank you, Chok, for this talk. So I have received quite a few questions. I think Shuangyang also received some. So Shuangyang, can you help the attendants for the questions and ask talks?
Sure.
Yes, thanks.
Thank you, Chok, for your presentation. There are quite a lot. There are several questions regarding OTFS in general, and some of them specifically related to the neural network design. So if you don't mind, I would like to answer some like a very general question. What is OTFS? The S stands for, because people are talking about that in the chat. So I guess that you can have a good answer.
Okay. This is orthogonal time, frequency, space.
Right.
Okay.
So
and
why there is a space?
Yes, space. And this is an issue I think many people try to figure out. What does this stand for? Right? In Ofdm, it is orthogonal frequency division multiplexing. In a synonymous way, is there a very simple answer to say what is OTFS? It is orthogonal time, frequency, space. And the space is corresponding to the environment. Space is corresponding to the environment, not necessarily the antenna. In the case of MIMO, space refers to the antenna. Here, I think we should see the space to be the environment around us. And their representations can be in very low dimension because of the compactness of the environment represented in the channel response. So they are compact.
Yes, yes. Thank you for your answer. Okay, so there are also other questions regarding the specific work. For example, like you mentioned, the phase noise in OTF for using OTFS to combat phase noise. So could you please explain why OTFS is less sensitive to phase noise compared to OFDM?
Okay. Okay, so it is, see, if there is a question related to Doppler, it is easy to see because intercarrier interference will happen in high Dopplers in Ofdm, so it performs poor. But why in IQ imbalance it works better? Why in phase noise it works better? We have to really ask more detailed questions. Inherently, the OTFS waveform is a natural waveform for channels, and the real reason why it works, I think, needs more understanding. But as of now, what we can say is it's a better waveform design,
yes,
which is quite natural to an environment that we are talking about.
Yes.
That is for Doppler. But for phase noise, for IQ imbalance, wherever we try to compare, OTFS comes as good. So even for zero Doppler, it is better than OFDM.
Right.
And there are papers written why it is happening. But then for phase noise, we have not seen a paper why it is happening. So those are things which we may have to understand better as we go along. But any experiment that we do comparing previous waveforms and OTFS, we always get good performance for OTFS.
Yes. I just want to add a little bit more on what Professor Chokes just mentioned. I think the phase noise, actually, I remember there is a paper talking about the IQ imbalance actually has a very special structure in the delay-Doppler domain. And I think maybe that's somehow relates to this question, why it performs better using OTFS. Yeah. Okay. Also, they're asking, is there how to perform the IQ imbalance composition at the receiver side in the presence of time varying channel? Is there a challenge for doing that?
See, IQ imbalance is nothing to do with the time varying channel.
Right.
So IQ imbalance is something to do with the hardware. And that hardware imbalance is due to your fabrication of the devices.
Right.
INQ may not be perfectly orthogonal. INQ gains may not be the same. So it is more of a hardware issue. Channel may not be a criteria in this IQ-I imbalance. So having said that, once a device is manufactured, and in fact, if you see our specification in Wi-Fi or even 5G or 4G, the EVM is the specification. Error vector magnitude is a specification for the transmitter as a whole and for a receiver as a whole. So as long as you meet that specification, you are fine. And these IQ imbalance variations are not going to be time dependent in a big way. They are going to be static for almost the entire life of the phone or the base station hardware. So all you have to do is probably learn that and compensate it and then leave it. So channel as such will not be a criteria in IQI compensation.
Right. Yeah. Thank you for your answer. There are also some questions regarding the DNN. So for example, there are people were asking how is the complexity defined in comparing ML and the DNN? Is it based on the number of adders or and the multipliers?
Okay, so I'll tell what we have been doing and we have been submitting when we submit papers. We've been asked this question. So we count the number of real operations as the measure. The numbers that we have put are number of real operations, and be it multiplication or whatever, but number of real operations we count, and that is the number that we give.
Okay. Okay. Also, is there an extension of the current scheme for the neural network? Because since the currently is only based on the QPSK case, can it be extended to the QAM or like, for example, like 16 QAM or PSK with a higher modulation order? Is that possible?
Yes, yes, definitely possible. But then what our experience has been, for each of these modulation alphabets, we have to train a network.
Okay. So
it is not having it is not going to be a single network for any modulation.
Right.
The number of parameters, hyperparameters that you are going to define and then train are going to be different. If you see my slides, I've put 3 columns, one for BPSK, one for 4 QAM, one for 16 QAM, and their definitions of that networks are different. So which means by and large, you go by trial and error. In fact, for 16 QAM, the observation was we needed a little more depth in the hidden layers and number of neurons in a given layer and so on. So it can be done, but at least the initial phases of development, it needs more trial and error and learning by ourselves how to use this DNN tool to suit our purpose. But it's definitely possible.
Yes, thank you. I think that's a really good answer. There are other questions regarding the general OTFS design. For example, there were people asking, is it really fair to compare OTFS and the Ofdm because in the current literature, most of the results are based on uncoded cases. However, with a large code and possibly interleaving, there also a spreading in the Ofdm counterpart. So is that will be a difference for the performance of OTFS or Ofdm?
Okay, so the first of all, is it fair to compare? I would not give a direct answer. It is an existing waveform. It is natural to compare. Okay.
Yes.
So fair or unfair doesn't matter. As long as one is good than the other, we can take it. At what cost? If that cost is affordable, we should take it, right? So OTFS Ofdm is natural comparison because OTFS is the newer one which is coming off the block, and the earlier OTFS is not the first one which is to come and compare with Ofdm. We talked about this filter bank based modulation schemes. We had GFDM, generalized FDM, with different pulse shapes and so on. So it has been there. The beauty about OTFS is it is phenomenally different and consistently different, better. Right. So that is the point. So it is okay to compare. It's nothing wrong in comparing. If OTFS is better, so be it. If Ofdm is better, that is also fine. And it is the community at large is going to benefit if one is good, and we are going to choose a better one. But answering the other question that coded versus uncoded is a classical question which comes again and again, which I have a very good answer or a standard answer. I would say not good answer. I would say a standard answer. If there is a system which performs in an uncoded setting, right, that system by good design will be made to work better in a coded system as well. Okay, let me repeat. If there are two systems and one system performs better than the other in an uncoded setting, right? If you do engineering and the design correctly, I can make these two systems in such a way that the system which worked in the uncoded case to be working better in the coded case as well. But suppose on the other way of looking at it is, if there is an inferior system in the uncoded case, and by coding you have improved it using a certain rate, but this new system which is doing well in the uncoded case, I can achieve the same performance by having a higher code rate. Instead of rate half, which you would use or need for an inferior uncoded performance system, I may use rate 7/8, rate 3/4, which is going to be giving you higher throughput and sometimes even better performance. So this has to be looked at, because Ofdm repeatedly people will say, we will do coding across subcarriers, we will do interleaving and so on and so forth. I think that is not the issue here. Ofdm, the very fact that high-Doppler it is going to be not good is a natural issue. So any amount of coding and other things, who is going to do the channel estimation? Right?
Yes.
We are doing OTFS channel estimation because it is slowly varying in delay-Doppler domain. So that is the benefit. So there is a reason of coded, uncoded question is okay. But then the bigger question is, in a higher Doppler, right? who is going to sustain OFDM?
That's right. Yeah, I think that's a really good answer, and I totally agree. As you mentioned, that maybe applying OTFS gives more freedom for the channel coding. Maybe I can use a higher rate to have the same performance. I think that's probably the beneficial benefits of using OTFS here. Yes.
Yes.
Yes. I think that's most of the questions are done, and there were some people just asking some new questions in the chat. Maybe I'll just due to the time limit, I'll just mention one or two of those questions. For example, there were people asking how to do symbol synchronization and frequency offset composition at the receiver side for OTFS.
Okay. So these are research topics.
That's right.
If you see some of the newly written papers, they talk about synchronization issues. Okay. One can argue that standard frequency and time synchronization techniques that are done for classical other communications may have to be done here also, is one view. Okay. But we are making a very broad statement by saying that there may be definitely benefits of processing in the delay-Doppler domain. Because whatever we have been talking about was channel estimate, timing estimate and frequency estimate and offset corrections. They are all classical approaches and time domain view. But delay-Doppler view, some of the early papers which I see on synchronization, they take advantage of the delay-Doppler nature of the system. So it is open. I would say I do not have an answer. We do not have any work on that direction, but I'm seeing papers being written, at least few initial papers. You may gain some things if you do such estimations, taking advantage of the delay-Doppler domain. As such, I do not have any immediate idea, but I think there may be good approaches using delay-Doppler signal processing.
Yes, I think that's a good point. Maybe just one last question. Is there any chance to use other neural networks for the design? Because currently, all the results are based on DNN. Is that possible to use, for example, CNN or RNN?
You will see more and more papers, definitely. You will see more and more papers from many parts of the world, because it is a natural question, and which I think, recurrent neural networks, right? They are good for tracking time series, right? Recurrent neural networks are good for tracking time series. So time varying channels are having correlations in it, and then tracking them will be natural for RNNs. So definitely CNNs and RNNs and combinations definitely will be, there will be papers coming again and again, I think. So DNNs may be the anybody's initial toy to play with. But as we go along, then we'll be a little more smart, and then we'll say, okay, other architectures are as good. And the community of communications and systems, people have to play with it. And OTFS is a good excuse, because you can now see that Doppler is a focal point, and it is good for the CNNs and RNNs to be playing a role there.
Yes, I think that's a very good answer. Thank you. Thank you, Professor Chokes.
Thank you.
Yes. Do you want to say something more, Vijay? Because I think we have pretty much covered all the questions so far.
Yeah. Thank you, Chokes, as Professor Emmanuel with say. So thanks for your nice talk, Chokes. Yeah.
Thank you.
So it is a real pleasure, and thank you very much for inviting me. And I hope to see more activities on OTFS and this special interest group. Look forward to read many such papers from this group. Thank you.
Okay.
Thank you.
Yeah. Thanks all in this event, and we will organize some more activities in the following months.
Yeah. Thank you so much.
Yeah.
Thank you very much.
Okay. So
yeah, thanks all.
Okay. Thank you all.
Bye.
Bye.